So today we're going to talk about the Lagrange remainder for a Taylor polynomial approximation of some function f of x. So the idea is that what we've been assuming so far is that when you write down a Taylor polynomial for a function, you get an approximation to the function, and we hope a good approximation. And we've also said that if we then continue the process so that instead of a Taylor polynomial, we're taking a Taylor series, like an infinite Taylor polynomial, then we've stated that the Taylor series for a function actually equals the function. Unfortunately, it turns out that's not always true. There are functions for which their Taylor series does not converge to them. Now, the usual kinds of functions that we encounter are perfectly fine, and their Taylor series do converge to them. But there are such things as functions for which that's not true. It turns out it's going to be fine for all the ones that we've claimed work. Sine of x, right? Its Taylor series converges to sine x. Cosine x is okay. E to the x is okay. 1 over 1 minus x is okay, and so on. So we're not going to worry a whole lot about that, but we do want to at least take a look at something called the Lagrange remainder, which it has sort of two really big uses. One is to verify when a function actually has a Taylor series that converges to it. And the second related point is that it is a way to estimate how accurate a Taylor polynomial approximation is to a function. So if we're going to use a Taylor polynomial to calculate something that's otherwise difficult to calculate, we want to know how much error we should expect in that approximation. So I started with the sort of general setup. We have some function f of x. Hopefully some of this notation is going to be familiar. The Taylor polynomial of degree n is given here. So remember, we take f of 0 and then f prime of 0 times x and f double prime of 0 over 2 factorial x squared all the way out to the nth derivative of f at 0 over n factorial times x to the n. Now, the Taylor series we're talking about here is centered around x equals 0. All of the ones we will discuss are going to be centered around x equals 0. So I don't always state that fact. But the hope is that once we form this Taylor polynomial, right, this is the sort of best possible nth degree polynomial approximation to f of x. And we sort of emphasize that that's what we're doing here, right? The Taylor polynomial is approximately equal to the function. All right, now what's new today is that we're going to talk about how far off we expect the Taylor polynomial approximation to be from the function. And we represent that by taking f of x and subtracting its Taylor polynomial. And then what's left, we call a capital E for error. So n for the degree of x. So this e sub n of x, this is new, but it's just the difference between the function we're approximating and the approximation we're using. Right? We want that to be small in order to have a useful approximation, but it unfortunately isn't always the case. Now, the main result here is called the Lagrange remainder theorem. So I'm shortening that just to say by Lagrange. There exists some point C which allows us to write the error like this. In other words, the error involved in approximating f by its Taylor polynomial, it turns out with a fair amount of work, you can show that it has this form, where you just take the next derivative of f, evaluated at some point C, which we don't necessarily know and can't necessarily find easily. But the remainder has this form, right? So the next derivative of f evaluated as c divided by n plus 1 factorial times x to the n plus 1. So it looks a lot like the next term in the Taylor polynomial approximation, except instead of a 0 here we have a c, which is something that's unknown, but it's stuck between 0 and x. So let's do a quick example to see how we might use the Lagrange remainder in practice. All right, so let's say our job is to approximate the sign of 0.3 with its Taylor polynomial. Okay, so I've written down the fifth degree Taylor polynomial for sine of x, and so the sine of 0.3 should be roughly 0.3 minus 0.3 cubed over 6 plus 0.3 fifth over 120. And I'll let a calculator do that for us. Get about 0.29552. All right, so I left off, I rounded a little bit, hopefully that'll be okay. But the idea is that sine of 0.3 is about equal to 0.29552. So the Lagrange error can help us figure out, without having to check, right, how accurate that approximation is. So the Lagrange remainder theorem says that that error, so the error involved in the fifth degree Taylor polynomial at 0.3 is equal to the derivative of, well, in this case, we know the function, it's sine. So the derivative, nth derivative of sine at c times 0.5 to the sixth over 6 factorial. Right? That's the form here. N plus 1 factorial is 6 factorial. X to the n plus 1 is my 0.3 to the sixth. And then we've got the sixth derivative of sine, so instead of that capital N there, that's 6, and it's evaluated at some point c. Okay, so we don't know what this value of c is, nor do we know the sixth derivative of sine, at least we haven't talked that through yet. But we know a lot about this because the derivative of sine, no matter what derivative we're taking, it's either sine or cosine or minus cosine. Right? That's the pattern we saw when we cycled through the derivatives for the Taylor polynomial. So whatever this error is, it's got to be less than or equal to the absolute value of plus or minus sine or cosine of c, and then that's all. Let me start a little lower so I run out of room. So the error at 0.3 is less than plus or minus sine c or cosine of c times 0.3 to the sixth over 6 factorial, which is 720. And then the last point is that regardless of whether we have sine c or cosine c on the inside, this absolute value, and regardless of whether it's plus or minus, the largest it can possibly be is 1, because both sine and cosine are stuck between 1 and minus 1. So this is less than just 0.3 to the sixth over 720. And that error, let's see, so 0.3 raised to the sixth divided by 720 is 0.00000. So we get 5 zeros and then a 1. So this is telling us that the error involved in the approximation using the fifth degree Taylor polynomial at 0.3 is less than 0.000001. It's a really good approximation. If you check with your calculator just to kind of verify and take the sign of 0.3, then we would get 0.29552, so it matches exactly with what we have there, and then a 0.20666. So it's almost exact. Lagrange remainder gives us confidence that that's the case.